Last time we nearly finished the op-amp anatomy, or the insides. I've got a little bit of extra stuff that I want to say, and then we'll have a look at a couple of examples, but I don't want to spend too long on them. It's just so that you've seen some circuits which are feasible. Even the op-amp circuits that you see in the data sheets of the op-amp aren't the real circuits, they're still simplified. Generally speaking, the manufacturers will not give away their schematic diagram. Even if they did, they wouldn't be giving away their IP, because you don't know what dimensions the transistors are that they're making on the chip, and you don't know what the chip's actually made from. You don't know the doping densities and so on and so forth. You don't know the characteristics of the individual transistors. Once we've finally kicked the internals of the op-amp out, we'll have to have a look at some aspects of the op-amp that we haven't considered up till now. If you look through all the diagrams I've been giving you, there aren't any frequency-dependent components, and that's done on purpose in order that we can look at the circuits in a more simplified form. To look at everything all together is quite confusing, actually. There are many effects which aren't readily explained without having some prior knowledge. But you will get to hear in the fullness of time all the frequency-dependent fun stuff. Not from me, though, from somebody else. Unless they give me another course, and I'll stand up at the end and go, so you shan't see me again, and then I'll just pop up next year, like a garden gnome or something. So we'll have a look at those, and that's number 3 on this list, and that will probably take the next 3 or 4 lectures. But I did say that about the op-amp anatomy, and that's ended up taking 5 and a bit, so... This is our final op-amp circuit that we like. We've seen this before, this is from year 3 as well. And I didn't actually get a chance to describe the next slide, which lists the improvements. So, IE and IVAS and IT9 set up the DC or quiescent conditions by defining the currents. So they are this current source, that current source, and that current source. And they allow us to choose the quiescent currents without having to worry about a change in the voltage drop across the, well, a big change in the voltage drop across the current source, changing the current that it produces. The current source provides a constant value, more or less. Whereas if we were using a resistor, we'd have to go, well, if the voltage across the resistor changes, so will the current. Not a very constant current source if the current changes with the voltage. Now, the current sources are usually mirror circuits. So we did the mirror as well, but I actually provided you with a current source that was made up of a couple of, it was a biasing voltage and a transistor and a resistor. And I said, that's a current source, let's have a look at the output impedance looking into the collector, resistance. Output resistance. Actually, that current source is pretty rarely seen. There are lots of things that aren't very good about it. And you still need a resistor, and you need to fabricate some sort of biasing arrangement, which could be a potential divider, or you could use a Zener diode and a resistor, or you could use a couple of diodes that are biased, and there are lots of options. You can just Google current source, I'm sure loads and loads will come up. Actually, they don't tend to turn up very much, because they have some problems. But also we can use a mirror, and if we do use a mirror, we can use a mirror to mirror a mirror. You'll see this in a bit. And if you put a resistor in the right place, you can choose a ratio of currents to flow through the mirrors. So you can have a mirror for this stage, which gives you, say, 5 milliamps, and you'd mirror this current somewhere down here in a circuit that doesn't exist, and mirror it back to there, but you put a little resistor down here in just the right place, so that you could choose, if this is 5 milliamps, this will be 500 microamps. And if this is 1 milliamp, this will be whatever the same ratio is. I've forgotten the numbers I already said. It's far too early in the morning. So there are reasons you might like to do that, because if you've got some chip-to-chip variation, and you just want the ratio to be right, it doesn't really matter about your variation, it's the ratio that's important. And with individual current sources, you can't manage that. Is that a what's going on? Have I lost you already?
No.
Okay, cool. If I have, then please say so. because if you've gone at this stage, then it's going to be a bit of a snooze. So, mirrors can be connected together on number 3, or point number 3. Mirrors can be connected together to allow the ratio of supplied currents to be set. And the simple current source doesn't allow you to do this. IE is typically 10 to 50 microamps, and IVS is typically about 10 times that, or perhaps a little less, and IT9 is a few milliamps. IT9 has to be bigger because it has to supply the base currents to the output stage, and the output stage has to drive the load, and we don't know what the load is because the person who's designed the circuit with the op-amp will be plugging the load in. Maybe it'll be a kilo ohm, maybe it'll be 600 ohms, maybe it'll be 50 ohms, 75, depends on the application. 50 ohm for a transmission line, 75 for a TV, 600 for some audio stuff, kilo ohm, could be anything. Lots of different options. And on the data sheet, the op-amp will say what it can drive. It will say full power into so many ohms. And usually you'd buy an op-amp specifically for the purpose you had. So if I knew I needed to drive a 50 ohm transmission line, I'd buy a line driver op-amp, and it would have some extra stuff that was good about it, like it could have a big capacitance hanging off its output, because a coaxial cable is just a long capacitor really. Well, okay, that's a gross simplification, but just looking down in, you've got a conductor in the middle and a conductor around the outside, and they go for a long distance. So you've got a D and an area, and a dielectric constant in the middle, so really coax looks like a capacitor at lower frequencies. And if you bought an op-amp that was specifically meant to drive such a line, it would be able to handle that capacitance, because the people who designed the op-amp will have made it so. There is no need to worry about that. So the improved circuit, which is on the prior slide, reduces all of the problems that I enumerated right at the beginning of when we were looking at the anatomy. But it is only one possible implementation. It's a circuit that was dreamed up by one of my colleagues some time ago when we started writing this course, because he said, I think it covers everything we ought to teach. I went, all right then. I could have come up with any other circuit. It could be that this stage here, I could have made it push-pull, ditched that, and that stage would have been 180 degree conduction per transistor, and this stage could have been 180 degree conduction per transistor. I could have popped that into there as well, that would be fine, as long as I adjusted the voltages. This particular circuit has no special significance. It's not a gold standard, it's just one of thousands and thousands and thousands. So don't hang your hat off it or anything. The last thing to say is, notice the general lack of resistors. I say that, actually I've still got 5 if you count the load, so 4 really. We could have done a lot better, especially for a circuit that's this simple. Sorry, but it is. And when we look at some of the layouts that are given on data sheets, there are far more transistors and far fewer op-amps. The designers will always want to use a transistor if they can, because transistors are cheap and they're probably going to make them anyway. If you want to put a resistor even, in your op-amp, you have to put in a couple of extra processing steps, and generally speaking, if you want a particular value, you have to trim it with a laser, and that takes quite a long time, and it costs more money. And those aren't things you want in mass production. It has to take the shortest time and cost the minimum per unit that you can manage. But I couldn't put everything I wanted into one op-amp, because there are lots of ways of doing all the individual bits. There are 3 stages. I could have had an output stage that conducted for 360 degrees of the cycle and only used 1 transistor if I'd chosen. Power dissipation would have been a lot bigger, but that's by the by. There is another circuit I didn't manage to squeeze in, which you ought to know about, because you'll see them now and then, and it's the cascode. And this is a connection of a common emitter amplifier to a common base amplifier. So the common base is T2 and the common emitter is T1, and in this case it's degenerated, but that's not really a big deal. I have assumed that there is some biasing network in V1 and V2, which is made up of some resistors, and we'll just take it as read that there's bias. All you really need is some potential dividers. 3 resistors in a line will do it, as long as you set up your voltages properly. A scratch or a hand? A scratch, righto. All bears need a good scratch. So the cascode is important because it enhances the bandwidth of the common emitter amplifier. And it does this by preventing some feedback that we previously haven't discussed. In the small signal model for the op-amp, there are in fact, in the small signal model for the transistor, there are in fact some capacitors, and one of them, it's actually a bit more like that. You can get even more complicated if you want to. But the important thing at the moment, you don't have to learn this and it's not examinable, although it is coming eventually. CCB is a mechanism of feedback between the collector and the base. Just as we had a mechanism of feedback with this RE by putting a resistor in here and summing up the currents on this node, we had a current contribution from the collector and a current contribution from the base, both putting a voltage across RE, and as a result, the base emitter voltage was affected by a portion of the collector current flowing in RE because it produced a voltage across it. And that we said was a kind of feedback. Similar arguments apply to collector current flowing through CBC and adjusting IB, which flows in DC. Don't worry about CBE too much, it's just there for completeness. So this feedback can reduce the gain of our op-amp, and it can reduce the highest frequency, sorry, not op-amp, transistor. I can't get back to transistors now, this is gone. Reduce the gain of our transistor at higher frequencies, and we'd like to stop it from interacting with our circuit. So we can do this by making sure that there isn't any voltage on this node here, or any signal voltage. So I want no signals here. If there are no signals here, because there is only a very, very small signal here. If I had a signal voltage here, I could say, well, in terms of signals, this is minuscule, very tiny. So all the voltage across CCB is due to the output, the collector swing. In that case, the voltage, the signal voltage that's swinging at the collector will drive a current through CBC, which will interact with our base current, and it actually interacts in a way to make this signal current smaller, and that lowers the gain of the amplifier. To get out of this, we need to make this signal voltage swing disappear. But if we do that, we'll have no output, and that's not a very good amplifier. So we'll try and make this into just a current. And the way we'll do it is we'll put something off the edge of the screen which looks like a current amplifier, i.e. has a very low input impedance. And the very low input impedance, resistance, will allow us to drive a current into that node without having very much voltage swing on it, which is exactly what we want, because we need to get rid of the voltage swing to prevent the feedback through that little capacitor. So if you were doing this in small signal model terms, you could draw out the small signal model T1. You don't have to include the capacitors, just to work out the gain, it's fine. And you could then just bolt on the small signal model of T2, which would look the same except the emitter of T2 would be connected to the collector of T1. And you could solve all the equations and get an answer. But you don't want to do that. Well, you can, it'll be interesting to do it and it'll take you a little while and it might be instructive. But if you say, I want to look up here, what resistance do I see? Approximately 1 over Gn. Go back to the common base thing, look it up. If you can't remember it or just deride it. Only approximately 1 over G, and there is a component of what happens at the base as well. So you can say there is a resistance looking up there, which is 1 over Gm, and I will use this small signal model, but I'll just put a resistor here. Which will be 1 over Gm. So that's RCE for this transistor. You don't really need to worry about RCE, not in this case. So I'm not going to derive it, this is one for you to have a go at. Good exam fodder this. It's a nice size, just like the Darling, so it makes a good half a question. Wink. Anybody want to hear that again? Okay. In that case, let's have a look at some op amps. This one we saw briefly yesterday, so I'll zip through it again if you weren't here. We have a differential input stage made of 2 JFETs. We have an enormous current source. If you've got a bipolar op amp and you find a JFET in it and it's not in the input stage, there's a pretty good chance that it's there to form a current source. The reason is you can set up a current which is known from a particular JFET by connecting its gate to its source, and you'll get the IS for that particular JFET. And if you know the dimensions of that JFET, because you made the mask that made the JFET, you'll know what that IS is going to be. IS for a JFET is not small, like IS for a bipolar transistor. It's a value usually in milliamps. So all this stuff is a current source, and it's one of these current sources where you can deal with the ratios, because really this is one part of the mirror, and these are the other 3 parts of the mirror. And we've got a differential amplifier here, and this is a current mirror. And there's some degeneration in the emitters of the current mirror to try and ameliorate any slight differences between these 2 transistors. We have a Darlington pair, and there's a little degeneration of Darlington pair, and there is this resistor. This resistor is quite significant. They will be degenerating the gain of this to set a pole in a particular place, and we will come back to poles and zeros in about 20 minutes' time. This resistor has a particular job. I will give the rest of the packet to anybody who can give a decent answer for what its job is. If you don't know, it's one of those things you could sit for hours and look at. But anybody want to take a guess? Yes?
Something to do with the feedback, so like the 0.7 across the second transistor with the then you have the voltage across the resistor for generation.
Yeah.
So it's linked then to the first transistor. The gain effect of the current.
Unfortunately not. It's one of these things where it's a nice answer. I think it does deserve a biscuit for a good try. Help yourself. You have to know what to think in this case, and what you're supposed to be thinking is, if I need to turn off this transistor, I've got to get all the charge out of its base region, because transistors are really a charge control device. If I'm going to get all that charge out, it's got to go somewhere, and that means this transistor has to get all that charge out, it has to go up here somewhere. Actually, if we turn off this transistor, and we need so the current down here stops, the charge in this base needs to escape quickly, and the best place for it to get out to is into the minus rail. So this resistor is there to speed up the turning off of this transistor. I wasn't expecting you to get it, don't worry. That sort of thing will not appear in this course. But if you're into your audio, if you go down the audio books and you can get through all the rubbish about fuses that sound better in one direction than the other and that sort of business, no really, they don't. Gold wire from the socket to your amplifier, never mind the miles and miles of copper transmission lines outside your house. If you can get by all of that, there are some little gems, and that will increase your turn-off time for, decrease your turn-off time for this transistor. This business up we did have an answer for what this was, but since some people weren't here yesterday. What is it again? Diode. You want a biscuit for diode? Yeah. Biscuit for cat. One-handed cat. So this is a diode, and we've got 0.7 volts across here. This is base emitter junction, which is switched on, and we'll end up with 0.7 volts across here. The current in this resistor sets the current in this transistor's emitter, and therefore collector, because we assume the base current is 0. So we end up with 1.4 volts between there and there. And this is our output stage, which is a very classical output stage. The diode and C1, let's not worry about them for now. Slightly more complicated one. This is a good example of where there are mirrors all over the place. We have a fancy looking input stage, which I don't really want to discuss too much, but if you want to sit down and work it out, it's really quite clever. This is the LM741, by the way, which is not the standard 741 that's been around for donkey's years. It's a bit of a reboot, like the Chris Nolan Batman films. It's much, much better and grittier. So we've got a current mirror. So R5 sets up the current that's going to be in this leg, and the reason is we'll end up with 0.7 there, and this point's connected to this point, so this is 0.7 below this rail. On the other hand, we've got 0.7 here, and this point's connected to this point, so this will be 0.7 above this rail. So we've got the rail voltages, less 1.4 is the voltage across R5. Figuring out where to start's the hard bit. So that gives us a current in this leg, and that gets mirrored to this leg, except there's a ratio of the currents that are mirrored because of this resistance popped in to say hello. 0.7 across there, somewhat less than 0.7 across here, because the current flows in R4, and that develops a voltage across R4, and that voltage across R4 must be taken away from the 0.7. So if this transistor is really at 0.7, and it's got the current that's set by R5, this transistor must have a smaller VBE. And if it does, it'll have a smaller collector current because there's an equation for IC in terms of VBE, it's the exponential one. So that's how you do the ratio of currents through mirrors. This business here is a current mirror, and that provides our current source for our sort of quasi-differential amplifier, which is this lot. This business is just a current mirror, also degenerated by those two. We've still got a Darlington, and this is straight out of my circuit. Well, it says my circuit. I don't own it by any means. All of these styles of circuit originate from a person called H.C. Lin, who published essentially the standard op-amp. He just dreamt it up one day. I don't really know how it worked. There's probably a history of how it happened as well as a paper about it. And since then everybody's used that design because it's got so many benefits and so few drawbacks. So we've got a Darlington, and we've got a VBE spreader or an amplified diode or whatever you like, and we've got an output stage. The business of this transistor is to protect this transistor if we put an output on which is too low a resistance. And the way it does that, well, how does it do it? Any takers? Think about the current that flows in R9.
So does it prevent like a too large ID going into that other transistor basically?
Yes, it does. Why?
Because like, well, it will turn on, won't it?
Yes, it will.
If there's a large current flowing, there will be a big voltage across R9. They'll switch Q50 on.
Yes. If you didn't catch that, there's a lovely patch of warm air just here. If you didn't catch that, let's assume I put a too low resistance on here and I drive a big current into it. Q14 is very unhappy about this, gets quite warm, might blow up, and that's the end of our op-amp. The big current that flows through Q14 into our load, which is too low resistance, must flow through R9, and when it does, it will develop a voltage across it. And that voltage, if it gets to 0.7 volts, will turn on Q15, and Q15 will steal some base current from Q14. Some base current will go down there and end up going into the load. Or could end up flowing a quiescent current down there as well. It doesn't really matter where it ends up. And the theft of this base current will turn off this transistor a bit, because you put a VBE on and a certain IB flows. or you force a certain IB in and a VBE, which is just right, appears. You can't have one without the other. So the theft of IB means that Q14 is going to have to turn off a bit, which saves it from destruction. Similar arguments apply to this transistor here, Q22. Q22 will develop a voltage on its VBE G2R11, and then that will turn on and steal some base current from Q15, which will turn off this different Darlington pair. Turning off the Darlington pair raises this collector voltage, and that will cause Q20 to start to switch off. If you're unhappy about why the collector voltage has to go up, sit down with my little circuit and just put DVs on and figure out which way the voltages ought to go. Alternatively, do it for a common emitter amplifier. In the situation where you have just a resistor, if I start to, let's assume a quiescent current of, I don't know, a milliamp, oops, sorry, and if we made that 10 volts and now 0 volts, we'd have, oh, I have to have a resistor as well, won't we? What should we make the resistor? Let's make it 5k. So we'll have 5 volts across there. Yeah? If I turn off this transistor a bit, this current should fall, and if that current falls, this voltage will fall. And if this voltage falls, this node voltage on that node has to go up, because it has to get closer to 10, because there's less, this goes down to 4, because that goes down to 0.8 milliamps, then this node voltage has gone up to 6, 10 less 4. That's why it has to go up. Happy? Right then. Where does that leave us? That's pretty much it for that one. Anything you want to know about that? It's a good idea to sit down with, in my case, a beer and a pen and just try to digest them. Just staring at it probably won't help. So, now a bit of a daddy. It's huge! This is an E5532, and this was the standard op-amp in professional audio equipment for about 35 years. So it's a really, really well-loved op-amp, and if you're into your audio, you've probably got loads of them sat about and you don't realise it. It's actually not that much more complicated than the last one. We have a differential amplifier, and we have a current mirror. Ignore this for now, it's just a diode. And this mirror is controlled by this mirror, which in turn is controlled by this, well, this mirror controls this transistor, which has 2 collectors. That's not to say it has 2 connections to its collector, it's got 2 collector regions. We have here our VBE spreader, and we've got an output stage composed of this transistor and this transistor. No, sorry, that transistor. Pair of these. And we have a current mirror here which mirrors that current to there, and a current mirror here which deals with the VAS stage. Where is the VAS stage? That's why this particular circuit is actually on the board. Other than the fact that I wanted one with loads of transistors in just to freak you all out a bit. We are looking for a voltage amplifying stage. Can you find it? It's a trick question. It is there, but you are probably looking for a Darlington or a Cascade or something like that. Actually, the voltage amplifying stage, the clue is, if you look at the differential amplifier with 2 outputs, and these 2 outputs feed these 2 transistors, this business here and that mirror is actually a differential amplifier, and it is the voltage amplifying stage. It provides voltage gain, just like a Darlington does. The fact that it's differential doesn't really matter. We've got a differential output from our differential amplifier anyway, so there's no reason not to use both halves. if you want to. That's all I'm going to say about that one. Right, and that is all I've got to say about the anatomy of op amps. Anything you want to ask about it, speak now or email me.
Did it have a cut off on the two inputs there? Like there's two.
Yes, it does. Have a biscuit for cut-offs. These two, the question, if you didn't hear it, was: is there a cut-off on the input? There is. These two transistors are made up to look like diodes, and if you put more than 0.7 volts between V plus S, you'll end up in a situation where one of those diodes conducts. Now the best way to blow up an op amp is to force its inputs apart and try and give it some feedback, so you'll drive a large current in, and these diodes will turn on to prevent the destruction of these transistors. Well spotted. So there is, as I said in lecture 1 a long time ago, 3 parts to this course, and we have now completed the first part, which I think is about a third of the course. But having not actually written the rest of the course, I don't really know. Now I know what's going in the lectures. I wrote that months and months ago, but I haven't actually written all the lectures, which is why I keep giving you updated sheets. So the next part of the course is to consider what happens to op amps when they're in circuits. Now in 118 we did quite a bit of this where we were talking about inverting and non-inverting, and I gave you some multiple input op amp circuits which were subtractors or adders. And if you were in the May exam, I gave you an adder that was non-inverting, which was a new thing that you've never seen before. And a few people said, oh, it's an averaging circuit, and they got a really difficult mark. But it was only 1 mark. And if you were in that one and then you were in the reset, I gave you a transimpedance amplifier instead, with a similar set of answers. So we did some op amp stuff. But we never really worried about the frequency dependence. We always said that the op amp was perfect and it had gain at DC and it had gain at light frequencies, and the gain was the same, which obviously isn't true. And having been in the amplifier lab, can you see a theme emerging here? Everything's in the amplifier lab. Having been in the amplifier lab, you'll know that there's a gain bandwidth product. That is to say, you can have a certain gain and get a bandwidth, and if you decide that you'll accept a lower gain, you can get a bigger bandwidth, and if you need a higher gain, you'll have to accept a smaller bandwidth. And we will discuss the reasons why that is the case in the next part of this course. We will also have a bit of a chat about frequency response, bode plots, the significance of poles and zeros, and eventually we have to talk about the Miller transform, which very sadly is not what happens when I drink a light American beer. Miller Lite? Never mind, doesn't matter. It's not a very good beer anyway. Finally, we'll have to talk about some slew rate type stuff, which is time domain effects. So this is the first bit of the next third. The next bit of the next third is we'll actually talk about some circuits. So everything on the last slide is stuff that's to do with the op amp itself, before we put any components around it. This slide is, we will put some components around the op amp, like we did in 118, and we'll work some stuff out. And the components we choose will be based on what we want the op amp to do. So in this course, it's not just a question of we'll get some gain or we'll add up some voltages and that sort of business. Now it's, I want a particular frequency response. In fact, we will look at we'll look at an integrator, which is one circuit, a differentiator, which is one circuit, and a class of circuits called pole zero circuits. So in 224, have you done pole zero circuits?
Yeah.
When I say done, I mean studied. And you're on second order circuits as well, is it?
Yeah.
Not yet, okay, that's fine. Just started, right. There is no second order here. Second order lives over there. We will only worry about first order things, and the way I will contrive that to happen is I will only talk about an op amp that's got a frequency response that's to say its gain changes with frequency, its open loop gain changes with frequency. If I've got a circuit with no frequency dependent components, and I will only talk about a circuit with frequency dependent components if I'm assuming my op-amp has got constant gain over all frequencies, constant open loop gain over all frequencies, so there won't be any second order. If you want to stuff them both together, you'll end up with something second order. If you've got a second order circuit and an op-amp with a first order response, you'll end up with something that's third order. The orders just add up. So only first order stuff here, second order stuff elsewhere. But that does not mean that you ought to try to compartmentalise them in your mind differently. It's all one glorious whole of electronics. Yes, that's pretty much what I said there. So, in 118 I said AV was infinite, and if I didn't, I gave a number. I usually pick like 500 or something, because 500 is quite big compared to infinite, but it's not really close to infinite, but it's not really close to zero. So if you worked out the gain of an op-amp amplifier with infinite open loop gain, you might find that it was, say, 10, if you designed it that way. And if I said, well, what happens if AV is 500? You'll find the gain is 9.91 or something. And it's that slight difference that I was interested in. In this case, we will say that AV has a function of frequency attached to it. That is to say, it changes depending on the frequency that you're operating at. And we will say that it's first order. Now, it's not really first order. It's quite high order, and if you look at the number of transistors that are dashed about the diagrams up on the earlier slides, you can see if all of them have got two frequency-dependent components attached to them, the order is going to go up pretty fast. But usually we can say op-amps are about third order-ish, and most op-amps will be designed by the people who design the IC to look as if they're first order. And part of the amplifier lab was that we would get the rise time. This was day 3, exercise 1. Is that right? Yeah, you get the rise time, and then you can put, no, it's day 2, exercise 1. Get the rise time of the op-amp, work out what its tau was, compare it with the gain bandwidth product, look at the phase shift. Phase shift's 45 degrees, your rise time's 2.2 times your tau, and the gain bandwidth product all adds up. You can say, oh, it's first order system. Happy with that? Or do you want to hear that again? Sure? 3 things that make a system first order. Gain at 3 dB point must be minus 45, phase shift at 3 dB point must be minus 45 for a first order lagging system. For your op-amp, your gain bandwidth product must equate to your tau that's given by your rise time, and your rise time must be 2.2 times your tau. If all those things are true, you can say it doesn't matter what's in the chip, it looks like it's first order. And we will assume all of those things from now on. So we have a first order equation here, which is K and 1 over 1 plus S tau if you prefer. But I don't want to just say, oh, it's first order, let's all not worry about it. I want to make sure you're clear as to how it becomes first order. So I'm actually going to make it third order, and then we're going to work backwards. So we have 3 real poles. So is this system capable of resonance? Now we'll see who's really paying attention. Oh, you only just started second order systems, haven't you? Then you won't know the answer to that. Right, okay. If you've got real poles, that is to say, if you can factorise the denominator, if I multiplied all this stuff out, and I could still factorise the denominator and get real factors, that's to say not complex factors, I couldn't have resonance because my poles are real. If I've got a system whereby I can't factor this into 3 real poles, say I've got 1 real pole and a pair of complex poles, I will definitely be able to get resonance. There is no certainty there will be resonance, but it will be possible. Are you happy with the idea of resonance? And poles and zeros? Right. Well, I've got a diagram in a minute that's to do with poles and zeros. We will come back to this if it's still not clear. it's really, really important in circuit design to be very flexible with your between time and frequency domain, and when you're in frequency domain, to have a good feel for what's causing the poles and zeros. So this is a bode plot of the third order system, and it just so happens that I'm going to call it an op-amp. Actually, it could be any third order system that has 3 real poles. I have a pole here, and I'm saying that's 3 dB below that point. The fact that the line is very nearly straight is neither here nor there. And at this 3 dB point, I ought to have minus 45 degrees of phase shift. And if I have another pole here, well, the slope of this line will be 20 dB per decade. So for every 10 times in frequency, I should drop 20 dB in gain. If you don't like that, 6 dB per octave, where an octave is a doubling in frequency. At the second pole, I ought to have another 45 degrees lagging phase shift. Due to this pole, as long as I'm a long way past the pole, 10 times the pole frequency, I'll have the full 90 degrees of phase shift that it's going to give me. When I get to about 0.1 times the second pole frequency, I will start to feel the effects of the phase shift due to this pole, and by the time I get to the pole frequency, I'll have another 45 degrees on top of the 90 that I already had. And by the time I'm 10 times higher in frequency than the pole frequency, I'll feel the effects of the full 90 degrees of phase shift that this pole's going to give me. So then I'll be down to 180. And similar arguments for the last one. Happy with that or no? If you don't like the idea of all these poles and zeros all of a sudden, think about a circuit. I always found that circuits helped when I had to do maths. If you don't find it, you might find something else helpful instead. But I don't know what that something's going to be. So we've got some RC network. And if I said draw the frequency response of that, you can do it? Or no? Oh, I've left the rubber. Sorry. Should look something like that. We have some cut-off frequency at which there will be 3 dB less voltage than there is at low frequencies, and at that cut-off frequency we'll have minus 45 degrees of phase shift. This is what our op-amp's heading towards. So it will look like that system. If we switch the capacitor and the resistor around, we'd find that went up. Well, okay, not exactly. For this particular circuit, it does make a lot of, get this sort of thing in fact. And your phase will look like this. Those are supposed to meet there, but I can't draw. If you're feeling very unhappy about the idea of poles as a concept, either dig up MATLAB and try and draw yourself some 3D plots and see what happens, because the pole, it will go to infinite. But you have to have a pretty good idea of what you're doing to actually be able to produce those graphs. So as a learning tool, it doesn't really help. The pole is the root of this bit. That is to say, what do I have to do to make this bit 0? Whatever I have to do, that's where the pole lives. Similarly, if I had some J terms on top, or some omega terms on top, sorry, whatever I have to do to make the top 0 is the 0. And there are as many poles and zeros as there are different time constants, or different bits of omega 0, omega 1, omega 2, however many. And the poles can be real or they can be complex. Only complex poles can give you resonance. It's all in Stroud, if you're worried. So how should I read this bow plot? The bow plot's in the prior slide. So casting a pole and moving from low to high frequencies yields an attenuation at the rate of 20 dB per decade. So for that system there, this will be 20 dB per decade because it's the first pole, the first order system. There are no more poles than the one pole. Yields an additional 90 degrees of phase lag. So for this one here, we've got this phase shift. When I'm a long way past the pole, about 10 times in frequency, I'll end up with minus 90 degrees phase shift. And the phase lag at the pole frequency will be 45 degrees. So when I'm on the pole, that will be 45 that's there. The amplitude of the pole frequency will be 3 dB less than it is at the low frequency value. And the effects of the phase shift will extend approximately 10 times in frequency from the pole. So from 0.1 times omega 0 to 10 times omega 0. Passing a 0 when moving from low to high frequencies yields the same effect, but the amplitude, I say increases. It's increasing from a low value here. You can make circuits where it increases from a flat value and goes up because you can have gain, whereas in these passive circuits you can't have gain. And the other thing to note is that the phase doesn't lag, it leads. This is, I'm calling this my reference, and this is leading by comparison. You feel comfortable with bow plot. I ordered passive networks last year, so you've seen an amount of it. So how do I make my op-amp first order? Well, I've got these 3 poles, and I'm going to take this pole and shuffle it that way off the edge of the screen until this pole, which is my second pole, ends up on the 0 dB axis, which is a gain of 1. And if I do that, I'll have all this stuff under the white bit here is the area in which I can have gain. And for all of the area in which I can have gain, I've got 20 dB per decade, which is one first order system. So by giving up the blue area, which is enormous, I can make my op-amp look first order, but have lower open loop bandwidth and open loop gain. That is all that happens. We will choose, the designer will choose to move this pole that way. They call it slugging, sometimes. I will carry on this slide next time because we have to stop now.